Okay, so let us get started. Let me welcome you to this 10th lecture of our course on reinforcement learning at ASU. I'm going to share this lecture with Yu-Chao Lee, and it has to do with some work that we have been doing over the last month that relates very closely to concepts and algorithms that we have been using in this course. But it has to do with engrams, of which I talked in one of the first lectures, transformers like GPT, ChatGPT. Another large area of applications involving hidden Markov models, abbreviated as HMM, and also more generally about Markov chains, and how do you generate most likely sequences within these structures. And we have a paper that has been submitted to arXiv that you can consult. So here's my outline. First, I'm going to do some review on engrams and also describe loosely the problem of generating the most likely sequence. I'm going to discuss this in the context of dynamic programming and also suboptimal policies like greedy and rollout and so on. And then I'm going to make a connection with a vast area of applications, which is inference in hidden Markov models, state inference, inferring a sequence of states that are hidden from us, but we obtain some data which relate to those states, and we try to infer the sequence of states through statistical methods, which, however, relate to dynamic programming very closely, and some of the algorithmic ideas that we have been using in this course. It's a famous algorithm in this context called the Viterbi algorithm, which is used in very large number of applications. And we're going to discuss the principles on which this Viterbi algorithm is based, but we're not going to go too deeply into it. We're going to stick primarily to a Markov chain framework, and we formulate our problem of most likely sequence selection as a dynamic programming problem. We identify states, controls, policies, and so on, objective function. The objective function is to maximize the probability of the generated sequence. Like other dynamic programming problems that we have discussed, the computation is intractable. So there's motivation to use suboptimal algorithms, and we're going to focus on rollout algorithms that are based on some kind of greedy policy that I will describe. These rollout algorithms improve greatly the performance, and we will show you computational results that they achieve performance close to the optimum with the benefit of tractable computation. And we'll take a break here, and Yu-Chao is going to take over and discuss the computational experiments, some computational experiments with Markov chains, and then other computational experiments involving GPT that we have trained, and it's large scale, and we have some computational results with that as well. So let's talk about engrams. You recall that an engram generates a sequence of text strings. At the kth time, it has a sequence of a text string of n words, and it generates a new sequence of n words by adding one new word to the front of the sequence and deleting the word that's in the back of the sequence. So this defines a deterministic system evolution and the evolution is controlled by the choice of the next word. Now, an engram does not specify the next word, but it gives you suggestions. It provides transition probabilities, quote unquote, for the next word, and the engram will give you these numbers. It's like in your iPhone, it will give you likely next words, okay, when you're texting. So these probabilities are a suggested local measure of desirability for xk plus 1 to follow xk. So it tells you this world has probability 60%. So it's 60% desirable if you want to use this kind of loose terminology. Another world has 30%. Another one has 5%. Another one has 10%. And most of the words, okay, the English language has like 50,000 words. Most of the other words are given that have 0 probability. So these are suggested probabilities. Even though your iPhone is not going to give you numerical values, they are available to the software, internally to the software. And you have freedom to select the next word according to a policy of your choice. In other words, you can follow the suggestions of the Engram, but you can also choose your own. So think of texting, next word suggestions. Sometimes you follow the suggested words. Sometimes, because you have some other objective in mind, something else in mind, you choose your own words. So we're going to focus now on policies that produce highly likely sequences according to the suggestions of the Engram, starting with a given initial state, or a prompt, if you'd like, an x0. So given an x0, the Engram will suggest next words, and we want to choose a sequence that will maximize the probability of the overall probability of the entire sequence going all the way to the future. So this is a global measure of desirability, as opposed to these probabilities made available by the Engram, which are a local measure of desirability. So loosely speaking, this is our problem. And we tried now to formulate it mathematically and see what we can do with it. So we introduce an optimization problem of selecting, of finding a selection policy that generates the most likely sequence. So starting with some x0, this most likely selection policy selects the most likely sequence from beginning to end out of all the possible sequences that can be generated according to the Engram's probability, next word probability suggestions. So this most likely selection policy is the one that maximizes this probability, the probability of the next sequence x1 up to, of the sequence x1 up to xn given x0. Now, the Engram has a Markov chain structure, has a Markov property, whereby the probabilities of the next words given the entire history of the Engram up to that point depend only on the previous word, on the current word. So this is called the Markov property, and it defines a Markov chain where the state of the chain is this xk. So that means that we can write this joint probability as a product of probabilities like this. And this is a consequence of this Markov property, but also the multiplication rule of conditional probability, how we calculate conditional probabilities in sequential events. It's a fundamental rule you learn in the first couple of lectures in a probability course. And so the bottom line is that we maximize a sequence of events, each one happening at each stage. And we will view this most likely selection policy as being optimal. That's our optimization problem. And its advantage is that it plans into the future. It doesn't look to optimize the next word, but looks all the way to the end and find the best sequence possible. And now we are going to use dynamic programming for this. This is a dynamic programming problem. But then you're going to say, what is the cost function? In dynamic programming, the cost function is additive, okay? It's the sum of stage costs. Here we have a product. Well, we have a multiplicative reward here, a multiplicative value, because we maximize. However, multiplicative value can be transformed into maximizing additive value by taking the logarithm of the product. The problem of maximizing product of rewards is equivalent to maximizing the sum of the reward logarithms. Take the logarithm here, optimality is preserved by taking the logarithm, and the logarithm of the product is equal to the sum of the logarithms. So even though it doesn't look like a dynamic programming problem, it is dynamic programming problem, and it's just a matter of translating the dynamic programming algorithm by introducing logarithms, but we're not going to do that. We're going to work directly with products. On the other hand, like the dynamic programming algorithms that we have seen, they require intractable computation, so this is an issue here. So this is the problem. This is the approach we're going to follow, and this is why we want to look at suboptimal policies, particularly the rollout algorithm that has been a workhorse for this course. So are there any questions? Yes. What does intractable computation mean? More computation that you will ever live to see the end result. Okay. Intractable can be arbitrary. The intractable stuff that we're going to talk in this lecture, you haven't seen before. It's more intractable than you've ever seen before, okay? And if I'm wrong, you can tell me at the end. So intractable means exponential computation in certain of the parameters of the problem and so on.
Xi Engram, current Engram. So our state is Xi.
Our state is xk at stage k.
Yeah, it stays Engram. So
for the Engram, yeah, right. So just to explain a little further, in an Engram, we have a vocabulary, right? The number of words. Number of words in the English language are 50,000, in the order tens of thousands, right? And we are going to, so the only possible next words are 50,000. And the combinations of n words is 50,000 to the nth power, okay? So we're talking about something very, very big.
okay, another thing is how reasonable is Markov progress Engram, and then next n plus 1 round depends on the previous one.
It's reasonable in the sense that the Engram, like a GPT, will give you these probabilities. That's all it gives you. It doesn't give you any other probabilities. That's what it computes. So we're trying to make use of whatever it gives us, right? Have a question?
This question. So here Markov property tells us that we choose the next word. We depend on the previous word. That's what the Markov property tells us.
Right. Depends only on the previous word, not on the words before the entire history.
That's not how we write in English, right? Like the current word depends on maybe few words before as well, not just the previous word when we write in English. The current word also depends on maybe 2 or 3 words before.
I believe it depends on the previous Engram, the previous N words.
You choose the next word. This is just suggestions. And that's what the Engram gives you. If he were to give you, if it were more sophisticated, would give you other probabilities, that would change your problem. So we look at situations where we have to assume a Markov chain structure because that's what the Engram problem problem context gives you. Now, when we talk like a few slides forward in HMMs, then it's more clear. There are calculations involved that support this Markov chain structure. Okay, so this is our optimization problem. Roughly, this is what we're trying to do. We'll formulate all this mathematically a little later. And because of the intractability of the dynamic programming algorithm, we are motivated to look at suboptimal policies and a common suboptimal policy. In fact, a variation of that is used in ChatGPT. It's some kind of a greedy selection policy, whereby we select at each case the next word that maximizes the next word probability. Okay. ChatGPT also randomizes over when it generates all the beautiful stuff that generates, it randomizes over the next word. But we're going to consider this greedy selection policy where we generate deterministically the next word according to maximum probability. That's the greedy policy. Looks reasonable, okay? We're trying to maximize probabilities from here to the end, so we can't do this easily, so we just look one step forward. Now, the rollout selection policy uses the greedy as base policy, whereby at state xk, it selects the next word xk plus 1 that maximizes the greedy Q factor, where the greedy Q factor is the probability of the sequence of choosing as next word xk plus 1, and then using the greedy policy, the greedy sequence starting from xk plus 1 to the end, okay? So first step optimization, greedy after that. That's the Q factor, and the Q factor, which we maximize, and we get xk plus 1. We reach xk plus 1, we do the same, and so on, as you have seen multiple times in this course. And there are also variations of rollout, multi-step look ahead, truncated rollout, simplified combinations, and so on. We'll talk about this within the next slides. Another suboptimal algorithm that we're going to use is double rollout, which is rollout on rollout. In other words, it's the rollout algorithm, but using as base policy, not the greedy, but using the rollout based on greedy. So if rollout is one policy iteration, double rollout is 2 policy iterations. And then triple rollout is going to be 3 policy iterations, and so on. So now the thing to note is that the Engram itself is a very simple deterministic system. And these policies are deterministic policies. The problem that we have is deterministic. And as a result, we can use sophisticated variants of rollout involving multi-step look ahead, involving incremental rollout, some of the sophisticated multi-stage search algorithms that we discussed back in lecture 6, and they're also in your textbook. Okay. So now let me give you an example just to get you into the mood. This is a very simple example, has no significance. It's overly simplified. It involves a 1 gram with this vocabulary. So the Markov chain has 2 states, 0 and 1, okay? It's Engram. If it were 2 gram, it would have 0, 0, 0, 1, 1, 0, and 1, 1. It would have 4 states. If it were a 3 gram, it would have 8 states, okay? But this is a 1 gram, and it involves these 2 states. And we're going to start at state 0. Now, the probability suggested by the Engram is what you see here. At 0, it suggests that you go to 0, that you select 0 with some probability p that's larger than 1/2, and the complementary probability to choose 1. At state 1, it recommends that you definitely go to 0, okay? So that's the structure. It's all artificial, just as an illustration. So what's the greedy selection policy? Starting here, we use the maximum probability next selection, which is 0, because p is larger than 1/2, and 1 minus p is less than 1/2. So we go here, so from here, again, we choose that, and so on. So the greedy selection policy, starting from 0, produces this sequence, a sequence of zeros, right? Now, what is the most likely selection? The sequence that has the maximum probability. Okay, so let's suppose that that P is like P is like close to 1/2. Okay, so 1 minus P is close also to 1/2, but P squared is going to be close to 1/4. Okay, so so this sequence is less likely than this sequence, and then we got to where we started, and we can continue this reasoning, and we see that if P is close to 1/2, in particular P squared is less than 1 minus P, the most likely selection is 0, 1, 0, 1, 0, 1, and so on. Okay, and this is the calculation. What you compare the probabilities of the two possible sequences. And otherwise, if P is close to 1, then, okay, P squared is greater than 1 minus P, and the selection is 0, 0, 0, 0. Okay? Now, how do you calculate the rollout selection? With one step look ahead, starting from x0, we calculate 2 Q factors. One Q factor corresponding to this selection, one Q factor corresponding to this selection. So we go here, and then we use the greedy, which is 0, okay? And that's one Q factor, the probability of this sequence. And we compare it with the other Q factor, which is to go here and then use the greedy, which takes us here and here continuously, okay? So basically, we have to compare the probability of this sequence and the probability of that sequence, which is exactly what we compared with a most likely selection policy. The rollout selection is the same as the most likely selection. Regardless of the value of P, the rollout is always optimal here. The greedy is sometimes optimal, but sometimes it's not optimal. Okay, this just to give you the idea of what we're doing here, just to give you some context. Of course, this example is very, very trivial. Are there questions here? Okay, so like I mentioned earlier, an Engram with its suggested probabilities defines a Markov chain where the next state, the probability of next state depends on the past state's history only through the current state. This is the Markov property. And it has to do with changing adding just the one word at the front and deleting one word in the back. Now, notice the dimension of the state space. You have an Engram with a vocabulary consisting of Q different words. That involves Q to the N states, okay? So the state space can be enormous. Very quickly, it climbs to enormous levels. So that's the kind of situation we have, a very simple system, but very complicated computations because of the intractability because of the exponential growth of the state space. So now let's just make a few comments about a related context which involves a huge class of applications, inference and hidden Markov models. And the inference problem is mathematically equivalent to the most likely sequence selection, except we have to choose the transition probabilities properly to take into account the data. We have, again, a multi-stage transition process involving states x0, x1, x2, and so on. let's say up to a finite number, capital N, and we are given data, some kind of data about the transitions that go on here, okay? And we want, based on this data, to guess which is the transition that's most likely that have happened, okay? We don't know the actual transitions, but we have data about these transitions. We know the structure of the chain, and we use the data to calculate quote-unquote transition probabilities modified by the data to calculate the most likely sequence within this, multi-stage chain. So that's the problem, find the most likely path, condition on the data. Given the data, the probability, transition probabilities are modified by the data. So it's something like what you see here. The joint probability of the next state and the data that you have observed, given the current, given the current state. Now, the range of applications of this inference problems is very large. Speech recognition is based on HMMs, language translation. They're used widely in computational linguistics. The Viterbi algorithm and this area started with coding and decoding and error correction. There have been many uses in bioinformatics, and all of this is very well established. There's a lot of information on the internet, videos and so on that you can watch. In speech recognition, basically you're given a sound sentence, a sequence of phonemes, what's called phonemes, and you would like to infer the phrase that was spoken, the words, the actual words. So the states are the words, the data are the phonemes, and you try to find the sequence of words that corresponds best to the sequence of phonemes, to the sound that you have heard. Language translation, you have a phrase in English and you want to translate it into French, let's say. The English phrase is the data. That's the data, and the hidden sequence of states is the French sequence. And you would like to find the French sequence that corresponds best to the English phrase using a framework like this. Okay, from linguistics, computational linguistics, there's a problem called the tagging problem, POS tagging, parts of speech tagging, whereby you're given a sentence like this one here. You saw a beautiful fish in the water, and you want to label each word, whether it's a noun, a pronoun, a verb, what kind of part of speech it is, an adverb, a determinant, and it's not clear what it is. There are probabilities, of course. We know that beautiful is most likely an adjective, right? We know that fish is likely a noun, but it could also be a verb, right? You go fishing. So is likely a name, but it's currently a verb, like we saw, okay? But it could be a noun, like in chainsaw, okay? Or it could be a verb that means we saw something rather than see it with our eyes. Water, okay? It could be water, or it could be I water a plant, okay? So all of this, this problem deals with recognizing, inferring what is the tag, the label of each one of these words in the sentence. And here the data is the sentence, and the chain has to do with the states are of few different kinds, noun, pronoun, verb, and so on. Transitions from noun to verb, okay, have higher likelihood than noun to a determiner like the. So, and then of course, there is data having to do with relating. There are probabilities that have to relate with the data with transitions between different parts of speech. So all of this can be formalized, and this waits on the transitions can be calculated. They're like modified transition probabilities. And we're looking to find a sequence that maximizes the product of these weights. That's the, in a nutshell, the inference problem in hidden Markov models. So the Viterbi algorithm dates to the 60s. It was developed in a coding communication context. For large state spaces, the exact solution is intractable, finding the most likely path. And suboptimal shortest path type algorithms have been used, but the Viterbi algorithm is used in many cases because the state space is relatively small. What we're looking for here is chains that have very large state space, for which using the Viterbi algorithm or simple modifications, it's totally intractable, completely unthinkable to use that. We need more systematic suboptimal algorithms, and that's what we're going to try to do with this rollout ideas. So I'm not going to talk about HMMs in the next few in this lecture anymore, but the rollout algorithms that I'm going to discuss fully apply to HMMs. And like I said, the transition probabilities are replaced by data-dependent or time-dependent also weights. Okay, are there any questions? Okay, so now let's go into a dynamic programming formulation of the most likely sequence selection problem. So the starting point is a Markov chain with transition probabilities. We turn now to a mathematical model. Forget about Engrams, forget about HMMs. We're talking about now a mathematical problem involving a Markov chain with given transition probabilities. A selection policy, pi, is a sequence of functions, like we have considered so far in this course, which, given the current state of the Markov chain, determines the next state according to this function. So these are the policies. And given a policy pi, which may be time varying, and a starting state x at time k, the future states are completely determined by the policy. And they are also denoted by this expression here. What is that? Given x and given the policy at time k, this is the state at time m, okay? State at time m, starting at x and using pi. So look at this diagram here. Here's time and here's state. At time k, we start at state x, and the first state is this y k plus 1k x of, depending on x and pi. The next state is going to be this one, and so on. So this is the trajectory starting at x at time k. And we have the probabilities of this. So it involves k minus m, n minus k transitions, and we have the probabilities of these. And the probability of occurrence of the entire sequence starting at k using this policy and starting at this state x is the product of probabilities. That's what I have here. The product of the probabilities. The probability of the first transition times the probability of the second transition, third transition, and so on up to the end. Okay? So that's sort of like the cost function of a policy pi, okay? It's like jk pi starting at state x, if you remember a dynamic programming notation, except here that we are maximizing rather than minimizing. So this defines the problem, and we can go ahead and ask for the optimal policy. And the optimal policy is the most likely selection policy, the one that maximizes the reward function, which is the probability of an entire sequence. We denote it by pi star in the usual way. And It's the one that maximizes over all policies this probability to go from time k a state x. And we want to find that for every initial state and time, and we denote it by tk star of x. This is like jk star of xk, except that it's obtained by maximization rather than minimization. And there is a dynamic programming algorithm for finding these probabilities to go, optimal probabilities to go. So here's the algorithm. What do we do in dynamic programming? We go backwards, which is the offline training part, and then we go forwards to obtain the optimal sequence of actions. And that's the online play algorithm. So similarly, here's the offline training. This is the dynamic programming algorithm, but with multiplicative costs, starting from this initial, from this terminal condition and going backwards. So here, given this probability at time k plus 1 for every possible state, we calculate this probability for every state at time k by maximization of something that involves the current stage probability, and y is the action here, times the probability of the remaining sequence, starting from the next state y all the way to the end. But it's a product rather than a sum that you're used to, but it's equivalent to a sum if you take logarithms of both sides. Okay, and remember, taking logarithms of a product is the sum, gives you the sum of the logarithms, and optimality is maintained. Whether you maximize the logarithm or whether you maximize the probability itself is the same thing. So I've transcribed the dynamic programming algorithm in terms of probabilities. I could have written in the usual way in terms of logarithm, but this is simpler and more to the point. Similarly, once I have this optimal probabilities to go for every k and every x, I can generate forward the selections according to this formula. Start at x0, then select x1 star by maximizing here, then select x2 star by maximizing here, and so on. So it's the same kind of calculation, same kind of difficulty. It's equivalent to the usual dynamic programming for multi-stage additive cost after we have taken logarithms of the multiplicative expressions that define these probabilities, the policy probabilities. And what's the greedy policy here? This is the optimal policy, how you obtain the optimal policy. The greedy policy is this new bar. It produces the next state by maximization of the transition probability over all next states. In other words, instead of looking at the next state probability and multiplying it with the probability of the remainder, we forget about this P star, we set it to 1, and we just maximize the next word probability without worrying about this other stuff. This does not require any offline training. We just go to online play, and it's pretty simple. And for mathematical reasons, we impose the requirement that ties are broken according to a fixed rule because we want this greedy policy to be sequentially consistent in the context of the rollout theory that we have developed. So we have problem, states, actions, policies. The problem is deterministic, okay? We have a dynamic programming algorithm to generate the optimal probabilities to go, and we have a greedy suboptimal policy that's pretty simple. Any questions? Okay, so now I'm going to go into the rollout algorithm and why it improves performance. You've seen these diagrams before. There's a one-step look-ahead rollout selection policy that operates as follows. You start from the initial state, and after you have calculated a number of states and you are at the current state xk, you look at all possible next states, and you run the greedy algorithm from each one. And you calculate the probability of this branch, the probability of this branch, the probability of that branch. These are the Q factors of the next state selection. These are given by this formula here, right? Probability of the next word given xk times the probability obtained by the greedy selection. Remember, pi bar is the greedy selection. Okay? So this is the one-step look-ahead selection policy. And I'm showing here the two-step look-ahead selection policy. And it would be generally L-step look-ahead. It's what you have seen before. For two-step look-ahead, we look at all the possible states 2 steps ahead, and then run the greedy policy after that, and calculate the probabilities of all the paths, and select the path that gives you the maximum probability, move to the next state according to this path, and then when you get to the next state, you repeat the calculation again. And the Q factor that you look at are 2-stage Q factors involving xk and the next 2 selections, y1 and y2. So we maximize over y1 and y2 over all these states that are 2 steps ahead, find the optimal Q factor, and go accordingly to the next state. And now clearly there are also truncated versions of these algorithms whereby instead of calculating the greedy selection all the way to the end, you go only a few steps ahead rather than to the end of the horizon. There's simplified variants whereby we don't look at all the possible next selections, but we just look at the most promising ones. For example, the ones that have high probabilities, high conditional probabilities given X. So all of these games that we have seen in the context of rollout can be played within this context as well, because it's entirely a similar context. And now this rollout algorithm has a performance improvement property. We've talked about cost improvement as being the important property of rollout. There's here a performance improvement property whereby we show that the rollout algorithm gives you a higher selection probability than the greedy algorithm, okay? And with the way we prove that is entirely similar as for what we have seen before by induction. And the result holds because under the hood, there's a sequential consistency property, which the base heuristic has, the greedy heuristic is a policy itself, okay? It gives you consistently the same selection when it finds itself at the same word, at the same state at different times. So it has the sequential consistency property, and that's the key for why this performance improvement property holds. So I'm going to run through the proof and the algorithm and the argument, like I said, we have seen before. So we want to show that for the greedy policy, pi bar, and for the rollout policy, pi tilde, you have this inequality. The rollout policy performs better in terms of probability starting at any time k and at any state x. And this relation holds because for k equals n, these two are equal to 1 by definition, that of the dynamic programming algorithm. So let's assume that this property holds for k plus 1, for stage k plus 1. We will show that it holds for stage k. And this is the proof. And it's exactly the same proof as for the case of cost improvement for additive cost rollout algorithms, except it's simpler here, okay? It involves less complicated equations. we want to show that this is greater than that. So we're going to start with this, and we're going to show through a string of inequalities that's greater than this. At the first step, we write the dynamic programming algorithm for the rollout policy, which this PK, the probability of the sequence generated from time k from state x by the rollout policy is the next word probability, okay, which is this is the next word, times the probability to go from that next state, that next state to the end using the rollout policy. Now, this part here is greater than this part, the corresponding probability using the greedy policy by induction, the induction hypothesis, right? This part, this is the same as this. This is greater than this. So this is the way the inequality goes. And now we use the fact that to compute this rollout selection, we maximize the Q factor corresponding to X and the next selection. One of these possible next selections is the greedy selection. So by definition of the rollout selection, which maximizes the greedy Q factor, we have this inequality. And then by the dynamic programming algorithm for the greedy policy, we have this equality here. So it's very simple and easy to understand. Questions? Now, this guarantees probability improvement, but does not tell you how much the improvement is. Experience with the rollout algorithm has taught us that the improvement can be very, very substantial. This is due to the underlying Newton step in going from base policy to rollout policy. The Newton step is inherent also in approximation value space as well as policy iteration. Rollout is one iteration of the policy iteration algorithm, and it is a Newton step. And even though you cannot tell ahead of time how much performance improvement you're going to get, typically the improvement is very, very substantial. And if you're close to optimal, it becomes even larger improvement in relative terms. Now, the computational results that Yichao is going to show you shortly suggest that this improvement is very high. You recover the optimality loss in going from optimal going to greedy. You recover that optimality loss by amount of 80%, 90%, things like that. And the more sophistication you introduce into the rollout algorithm, like multi-step look ahead or double rollout, the better results you get. So that is going to be seen from the results that Yichao is going to present shortly. And let me say something about this double rollout. Remember the relationship of rollout with policy iteration. You start with some policy, you evaluate it. Basically, you evaluate its Q factors, in this case by forward propagation through the Markov chain. And then you improve the policy by maximizing its Q factors. That gives you the rollout policy. Now, this is, let's call this single rollout. Rollout with the greedy as base policy. Now, take this rollout and put it in place of greedy policy as the new base policy. You get double rollout. Double rollout is rollout with single rollout as base policy. After this has been put in here. Triple rollout is rollout with double rollout as the base policy. And kth order rollout is rollout with k-1 order rollout as base policy. And all of this can be done recursively in a loop. Of course, the higher the order, the more computation is involved here. But we have been able to do double rollout with no problem and with significant improvements. And triple rollout, it's possible to do it. And part of the reason that you can do this double and triple rollout and so on is number one, that the system is deterministic, so the calculations are simplified, and you can do truncation. You can use truncated rollout or simplified rollout. You can use all the tricks that you know about multi-step look-ahead optimization, and that can simplify the calculation. So theoretically, with every additional layer of rollout, there's an amplification factor of Q times N. N is the horizon, and Q is the number of possible next states, but after simplification. In other words, there may be 50,000 possible next states, 50,000 next words, but if you look at the next 10, then Q is 10, not 50,000, okay? And finally, a theoretical result that relates to policy iteration. If you do a large enough number of policy iterations, then you are going to obtain the optimum, the most likely sequence. But of course, we don't know ahead of time how many iterations you need for this to happen. It could be large, but you get very quickly, after one or two, you get very quickly to the optimum according to experience. So we're ready to take a break. Are there any questions? So let's break for 15 minutes. Let's start at 5:43, okay? And we'll get into computational experiments.
All right, let's get started. Now I show our algorithm in action and present some computational experiment we conducted. First, I will show the computational results for our method applied to small-scale Markov chains, where dynamic programming is still feasible, and we can compute the exact optimal most likely sequence so that we can assess accurately how well our algorithm perform. Then I would go to explain how we apply our method for inference, generating the most likely text string from a fine-tuned GPT, where computing the exact solution is not feasible anymore. For the Markov chains that we have applied our method, we consider with length up to 100 most likely sequence from a set of C of Markov chains involving 100 states. And for each state X, there are 5 states Y, from which to which the state can have non-zero probability. So conceptually, you can think that the transition probabilities are given as a lookup table. If we look at here, it's a lookup table, square lookup table with both row and column indexed by the states. And if we stare at the second row, then the elements are the transition probability from X to all the states in the state space. And for this problem, executing dynamic programming is possible, and that's what we have done. And because we have access to the optimal policy and most likely sequence, we measure the performance of rollout by what we call percentage recovery of optimality loss of the greedy policy, given by this formula. So this term is the geometric mean, or the average transition probability under the rollout policy. And this is the average transition probability under the greedy policy. And similarly, this is the most likely sequence and we compute its average transition probability and how far the greedy policy is from the most likely sequence would be the denominator. So using this metric, we measure how well our rollout method is. Let's look at the percentage recovery by rollout. As mentioned earlier, because even though we are considering Markov chain, but the problem itself is deterministic. We are computing most likely sequence. Therefore, everything is deterministic. As a result, we can contemplate some more sophisticated variants of rollout that would not be possible in stochastic context. In particular, we applied both rollout with one-step lookahead, as well as multi-step lookahead, up to 5 steps without truncation. So the simulation go all the way into to the end of the sequence length. So recall that sequence length is 100. So even starting from the very beginning, when we run rollout, we run all the way, we run the greedy heuristic all the way till the end of the horizon. But we also tried rollout with m-step truncation, where m only equal to 10. So it's relatively short. It's about 10% of the entire sequence. So we want to see how well it performs. And this is the result we get, which is average over 50 randomly generated Markov chain. Some general observation we can see from this figure is, regardless of what variant we have tried, rollout leads to substantial improvement over the greedy policy in all test cases. And second thing is longer lookahead results in improvement on average. So with longer lookahead and the percentage recovery is larger. So up until 5 steps, at this point, there's only less than 10% optimality gap compared with the greedy policy. And recall that from each state, there are 100 states in the state space. There are 5 next state with non-zero probability. So in one step lookahead, we compute 5, the tree have 5 leaves. We compute 5 times complete trajectory in this one step lookahead non-truncated rollout. Whereas in this case, we compute 5 to the power 5, much larger. I cannot calculate the answer in my mind, in my head. So much larger number of rollout need to be done. Therefore, it's even more significant to think about applying the truncated version. And luckily, what we have seen is that performance seems unaffected by the 90% truncation of the rollout horizon. So with longer lookahead, there are more leaves you need to run simulation starting from. And in this case, the positive, encouraging result we get encourage us to try longer lookahead, because this is a significant computation saver compared with untruncated version. Any question till this point?
Is the application on text generation, or what is the rest of it?
Okay, the question is, what is the application here? The application is now, or I should say, this is a academic example. I'm going to show next the text generation example. So in this case, you can just think it's Markov chain, and with 100 states, and each state can have non-zero transition probability to 5 different states, or probably including itself. And the next computation example would be a text generation example. Yeah, but this is for illustrating purpose to show the to access accurately the performance of rollout. Because in next example, unfortunately, yeah, you cannot evaluate. You can only see the improvement, but how far away from optimal, we don't really. Yeah. Okay. So let's look at some typical patterns occurred in our computational study. Every figure in this slide and next slides represent one Markov chain. So in the previous figure, the bar graph is average over 50 randomly generated Markov chain. And in this context, every figure represents one Markov chain. And the x-axis is different states indexed by 1 to 100 or 0 to 99, I don't remember precisely. And y-axis is similarly the average transition probability, but only average over the geometric mean over the length of the generated sequence. In this case, it have not averaged over the state space because different states. So because we want to look at the different patterns over different states. As I commented a moment ago, in this case, we can compute the optimal, most likely selection policy, and that is shown as dot blue curve or blue figure here. And this is the optimal selection policy resulted average transition probability calculated by the geometric mean starting from, let's say, starting from state 0. And using the optimal selection policy, you generate the entire sequence and you compute the geometric mean of that sequence according to the Markov chain probability specified by the Markov chain, and that would be this dot. And this orange figure is untruncated rollout with one step look ahead. And similarly, this blue figure is untruncated rollout with 2 steps look ahead. And the red one is with 3 steps look ahead. And the one on the bottom, purple, is the greedy policy result. As you can see from those 2 figures, what is common in those 2 figures is that both have substantial improvement from the greedy policy. All the rollout policy and its variants have substantial improvement over the greedy policy. But the difference lies in how much the increase of look ahead contribute to the improvement in terms of transition occurrence probability. And in the first figure, well, the improvement starting from the 1 step to 2 step and 3 steps, they all have some improvement, but somewhat they stuck at a range that is still slightly have a slight difference for distance from the optimal. Whereas in the second Markov chain, at the first, the rollout with 1 step look ahead is already fairly close to optimal, and with 2 step look ahead, so increase 1 step into the future in terms of look ahead minimization, this blue part is already overlapping with optimal in the majority of states. And what is kind of rare in our computation study in this figure is that 3 steps look ahead actually makes things worse in some states. As you can see, this red curve somewhere kind of the average occurrence probability decrease. And you may recall in the textbook, one of the textbook, there is a academic example also in deterministic context where increased look ahead actually results in the performance degradation. But I should stress that those two cases do not occur in our numerical study in equal proportion. So this is kind of a rare case, but it's representative of a class of situation. So similarly, or the pattern represented by this two figure are a bit more common in our numerical study. The first case, you can see there is a substantial improvement from the greedy to rollout with one step look ahead. But then there is almost equal amount of improvement for the second look ahead step. And then the third look, with two steps look ahead, it's almost, it's very close to optimal already. And the third step make it even closer. And slightly different pattern here is the three look ahead steps bring in almost equal proportion of improvement. So those two kind of situations are more common in our numerical studies. But what is common across all the test cases, which is consistent with the theory that rollout and its multi-step look ahead variant all have improvement, and the improvements are all substantial over the greedy policy. Yes?
The difference for these two figures, like the
yeah. So all those things are the Markov chain are specified by the lookup table with 100 states and so on. Yeah.
I'm curious about when, especially in the previous slide, like there's one significant spike for the greedy policy.
Yeah.
There. How do you like empirically interpret that? Is it like for that specific state, like any policy can achieve the best performance and what?
Well, not certainly not any policy. You can purposely choose at every state the smallest probability and just, do the opposite of what greedy is doing, and then the performance would be bad. Yes, it's correct that in this particular case, actually greedy policies for this particular state, the greedy policy is optimal. So how we generated the Markov chain is essentially with 100 state. We use uniform distribution to select for each state with uniform distribution to select this candidate 5 different states, which we assign non-zero probability. And then for this probability, again, we use uniform distribution to assign some numbers and normalize and make it a transition probability. So it could occur in some situation for some states, the greedy is optimal, and I don't really have more to say than this. Yes?
Do you have like any aberration study on the number of valid state transitions, like the number of plots?
So basically, we've tried from, in this case, the number of states from each state they have non-zero transition probability is 5%, right? And we tried from 1%, or 1% in this case is trivial because everything is deterministic, up to 5%, and we tried states from 100 up to 1,000, and it's pretty much consistent in terms of pattern we find, and in terms of bar graph we see. So, and we mostly have focused on the case where the number of states from each state, it have non-zero probability is relatively small and fixed, because we want to we want to focus on Markov chains that resemble the Engram applications we have in mind. And here, the number of non-zero transition probability would be not the number of states where you have non-zero transition probability would be the vocabulary size in the context of language text generation. Okay. Now let's get to a more sophisticated version of rollout, which is the double rollout. So as I mentioned earlier, because the problem is deterministic, we want to compute the most likely sequence and with the probability specified by the Markov chain, everything is deterministic. So we can actually run double rollout with one-step lookahead and multi-steps lookahead. Or again, the lookahead steps are from 2 to 5, which are denoted by hat here. So we try the rollout without truncation and with truncation, where the truncation M number is 10, which is the same as the previous case. And the green bar here show the results of double rollout, and we put the single rollout result with one-step lookahead here for comparison. Some general observation you can see from this bar graph is that double rollout and its variant lead to significant performance improvement over both the greedy policy, which is here, which is the 0 bar here, and the single rollout with one-step lookahead. So once you apply double rollout, all of a sudden you have another 20+% optimality loss recovered. And another significant or another exciting result is that the truncated version, just as in the case of single rollout, remains effective. And okay, there are performance degradation as you might expect, but it's relatively small and quickly recovered by longer lookahead. So, and recall this is M equal to 10 and the capital N is 100. That means we only simulate 10% of the trajectory and you get performance improvement this much, which is encouraging news because we can apply longer lookahead to improve performance even further. Any question here? Okay, let's get to the next topic where unfortunately computing the optimal is not feasible anymore, intractable, which is applying our technique to generative pre-trained transformer known as GPT. Transformer architecture improved in important ways on earlier neural networks by using the attention mechanism, which is well known nowadays. But I would gloss through some key ideas there. And such neural networks are often pre-trained with a lot of general purpose data before they are further trained or fine-tuned with special purpose data. And owing both to the architecture of the transformer, as well as the ability to be pre-trained, the resulting neural networks are often generative, being able to create new content or to perform open-ended tasks, which bring a lot of enthusiasm. And there has been tremendous amount of applications, natural language processing, computer video, image, and music generation. In fact, this figure is generated by GPT architecture. I just asked I just use the prompt, generate an encouraging figure for, inspiring figure for GPT application. And this is the vibrant figure it created. But we're going to focus on text generation and view GPT as an Engram. All right. So at the core of the transformer is this attention mechanism. And for this, let's consider this text string. Reinforcement learning is found, okay, as the input. The GPT we used view this text string as 6 different words. And the unit are also known as tokens. And as you can see, it's divide words in unusual ways. It's not the word unit we consider. So it divide reinforcement as 3 units, 3 tokens, RE, in, and enforcement. And then with learning, but learning coming before the word with this special special symbol that represents white space. So with the same word learning, with or without white space are two different tokens. And then comes is and found. So for each ordered word pair, like in and RE, or enforcement and in, and so on and so forth, it calculates a number called attention score, which measure the affinity between those 2 words, how strongly they are related. If we look at this sentence again, reinforcement learning is found. So for the enforcement, it will calculate the attention score between enforcement and in, and between enforcement and RE, and enforcement and itself. This is what we mean by feasible order words, at least in the application we have applied. So it's kind of implied this causal architecture of text string that when generating the next word, it can only depend on the previous words, which is precisely the Markov property we have. So then it compute this 3 numbers, and you can see from this heat map that it's mostly connected to itself, which is common, but also strongly connect to the first unit, RE. So this is the numbers it compute. And eventually for this input, reinforcement learning is found. It generates this heat map, this part, triangular part. And this affinity score or attention, affinity score would demand attention of the neural network. So the neural network would pay attention to the connections with higher score. And at core, this is how the attention mechanism works. And this affinity score is generated using the ways upon which we fine-tune our model. So if we look at how they are trained, again, using the text string reinforcement learning is found. This simple text string actually corresponds to 5 training data pairs with input and output, input and label. So starting with RE, which is the input, its label is in. And starting with RE and in, which is the first 2 tokens or word unit, its label is enforcement, and so on and so forth. So the input would feed into the GPT and would generate output of its own prediction. and how the output would be the probability distribution over the vocabulary, which I'm going to go to shortly. And then the label going to go to the training algorithm, and based on the label and the output of the current GPT, they're going to modify the weights. So this is the, in a nutshell, the training process. And what is unique or different from the conventional label data we have seen in previous era machine learning application is that the text string for training does not require explicit data labeling procedure, which is intense human labor. You can see it once it automatically divided into units or pieces, the input and label pairs automatically generate. This automatic generation of label data from unlabeled data for training enables the pre-training with large amount of general purpose data, because you just need to feed huge amount of text strings, and this input and label pairs can automatically generate it, and you have plenty of data to train the neural network. So this label data generation and training process are collectively known as self-supervised. The training algorithm we used for GPT off-the-shelf software, which at the core scaled versions of stochastic gradient descent, and some of the key concepts and ideas we're going to touch upon in the next lecture. As I mentioned a moment ago, the output of the GPT is a distribution over the vocabulary. Once after we fine-tune the GPT, we use it to generate text string with length 200. And the Engram model we use to view the fine-tuned GPT have small n equal to 1024. So this is how the output looks like. Given an initial text string x0, which we view as prompt, we go to the fine-tuned GPT, then the output would be a distribution over the entire vocabulary. And here I show the top 10. This is the output from our fine-tuned GPT. And the input is a complete sentence. And as I mentioned a moment ago, the special symbol represents a white space, which is reasonable because I give it a complete sentence, and it predicts the next most likely token or word is white space. Actually, with overwhelming probability, twice over a word. So yeah, this indicates how it works. But unlike the previous example where the transition probability of the underlying Markov chain is lookup table, this time we cannot draw a lookup table anymore. It's actually generated by this piece of software, which is the fine-tuned GPT. Let's go back to the topic of intractability. Now, to store this lookup table, to store the transition probability in a lookup table is not anymore tractable, because the vocabulary size is 50,000, and the context window, some would call the small n, is in the Engram is more than 1,000, and this is this many states in this Engram we study, which is enormous. So it's not even possible to store as integers for each state. So this is way too large, and it's not possible to compute. And what is worse is this large vocabulary size, 50,000, also leads to excessive Q factor computations. Recall that how exact rollout works is at the given state, it's going to compute Q factors with one step look ahead. They're going to compute Q factors, each Q factor representing one feasible next state. And each feasible next state corresponds to one element in the vocabulary, right? And this would mean if we execute exact rollout with one step look ahead, for each decision to make, we need to calculate 50,000 trajectory Q factors and run that many complete solutions, which is infeasible. So what we have done is instead we apply simplified rollout and its truncated counterparts, because if we look at some of the output transition probability, we see, okay, top 10 have overwhelming probability collectively, more than 99%. The remaining ones are just highly unlikely. We probably can safely discard them. And what's more is, as you know, the modern day language model in their training phase heavily rely on the parallel processing power of graphical processing units, and rollout can fully harness this power because all the simulation you have can run simultaneously. And in fact, based on the hardware you have, let's say you have a hardware which support 50 parallel computation to run, then you can just, instead of having simplified rollout with 10 look ahead, with 10 control to consider, you can have 50. Or you can try with 5, or let's say with 7, top 7 words for one step look ahead, and then top 7 for the next stage. So in total 49. So it would be 2 steps look ahead, but with simplification in terms of this minimization. So, and we have only tried with one step look ahead, but the result has been encouraging. So let's see. We applied 2 simplifications in our techniques. One is that computing only 10 Q factors corresponding to top 10 most likely next words. This is simplified rollout with one step look ahead. But in addition, we also tried truncating the simulation after 10 steps. This is M step truncated. From this figure, the general observation, okay, so this figure represents 20 different test cases, 20 different X0. Compared with the previous 100 state Markov chain example, I cannot possibly plot all possible initial states, right? That's 50,000 to the power 1,000. So I sampled 20 different initial states, how I did that. So basically from a GPT, pre-trained GPT, some of you might be familiar, this is GPT-2, which is relatively easy to handle, and we can modify according to our need. And we load the weight that is available, and we fine tune it with writer's writing, Michener's writing. And for the initial states, we basically ask GPT-4 with the prompt, provide us with 20 different opening sentences in the style Michener's writing. So GPT-4 gave us those 20 different opening sentences, which we view as initial states. So that's 20 different X0s. Then those sentences text strings would be used as input to our fine-tuned GPT. Conceptually, to make those sentences also Engram, we need to add additional placeholder elements to fill it up to 1024 lengths, because those initial sentences can be different lengths. And if we view it as Engram, we need to add the placeholder word into the text string. So it becomes an Engram or 1024 gram. But basically, we try those 20 different input and compute its average transition probability, the average occurrence probability for the generated text string. And this is how it looks like, where this blue figure is simplified rollout, and the orange one is its truncated counterparts. Were up to I think 10. So the truncated simulation is 10, so things like that. Yeah, 10 steps. And the observation we can see here is simplified rollout still have substantial improvement over greedy policy with modest computation increase. And the truncated counterpart still improves upon the greedy policy in all our test cases. Yes, please.
How do you think of in more?
Oh, here.
On the side,
Yeah.
you have like probing still X5, right? How do you compute it?
Oh, so as I said, since this is a this GPT, we have access to its probability like this figure. We have all those numbers available. Once we feed into this text string, we have all those numbers available. So all those transition probabilities are available, and we basically just record those transition probability and then multiply them together, similar to the Markov chain case. The only difference here is, okay, it's not a lookup table that we have all at once. It's computed on the fly. Whenever we put a text string, it generates stuff, and for each word or token generated, we also consult under the hood what is the probability corresponding to this token or word selected by our rollout policy, recorded. And then for the next token selected by the rollout policy, we record the corresponding probability and so on and so forth. And then in the end, assemble them, multiply them together. And another thing is, yeah, truncated counterpart still improves upon the greedy policy in all our test cases. Yes, please.
Fast function that we are talking about here.
Sorry?
Can you comment on the fast function that we are talking about here?
So the cost function here is, again, since we only consider, the subject we consider is generating most likely sequence, right? So we want to maximize the occurrence probability of the entire string of n-grams. And the cost function could be interpreted as minus of the transition probability, the collective probability of this string of n-grams. And if you want the additive form, you take a log. So this is the cost function. But if you remove that minus, it's a reward function, and you want to maximize the probability, right? Yes.
I kind of feel like when you do this, you're kind of embracing the biases most likely that is generated or modeled in the training process of the GPT. You have like an empirical example between the greedy policy and the
Okay.
rollout policy. Because first, sorry, let me try to make it clarify for myself. The 0 to 18 starting is like 18 paragraph, right? Like 18 paragraph of
Or 20. Yeah.
20,
Yeah.
20 paragraphs of 1024
Yeah.
tokens.
Yeah.
So do you have like a completed version of actual text for comparison? For example, like I know that right now, like after rollout, you can calculate the probability
Yes.
together.
Yes.
But does it really read really
Okay.
well?
So that's a completely different subject. And in fact, in terms of evaluating the quality of the generated text string, since that's not the purpose of rollout, so the rollout only do what it is instructed to do, which is compare numbers and find a large number and choose the control that corresponds to that large number. So it only compute probabilities and have no regard whatsoever about the quality of the generated text string. But there is not even a subject or objective definition of quality of the text string. The observation we have seen is that because how we view the problem and how the transformer, the GPT we have, we find that so in the vocabulary of the GPT-2, there's this special token called end of text. So basically represents the previous stories over. And we find once that token appear, all the subsequent transition probabilities would be fairly high. So our method computed text tend to be very short. So very short and try to find that text string and that's it. And alternatively, there could be other problems to consider, like instead of calculating the most likely overall sequence with fixed length, you can consider computing most likely sequence with average transition measured by average transition probability. But what you mentioned, whether or not all those things translate to the quality of the generated text string, that's a completely different problem. So
I can imagine several other situations where the quality are more easily
yes,
measured.
yes,
For example, like currently ChatGPT, like when you ask them several questions, it can give you like several format of basically the same answer. I
yeah,
assume that in those situations, if implemented through online rollout, you can just use a different model to basically measure how formatted, or in some other situations, how hateful this passage are generated, and then you can generate different stuff.
yeah. I think there are ongoing research about this kind of topic, and what we find difficult, at least in our experiment, is that when we compare the quality of generated text, even GPT-4 provides wildly inconsistent result from one round to the other, and it performs not consistent and not coherent, which make it to be used, or this quality to be used as a value function or as a measure of how well it performed become very difficult. So, but on contrary, the metric about the probability and so on is clearly defined. And I understand what you meant, that okay, it's biased towards this trend, but from our conceptual point of view, it's a Markov chain, and it's defined by this fine-tuned GPT. Okay, another related, somewhat related subject is, in training and actual operation of GPT, there are also some additional intermediate parameters and stuff you can tune, like for example, to suppress the generated text to be repetitive, you can install some filter to prevent it to say topics that completely beyond the context. You can include some other stuff, but all those implementations are done is doing is to modify this output probability. And what is important from our point of view is once the weights are fixed and once all those parameters are set, we are given a Markov chain, which is what we're going to operate on. So. Any other questions?
Sorry, I got one more.
Yeah.
The simplified rollout is saying that you don't want to do 50,000 new word.
Yeah.
Simulation, so you choose the max, like.
Yeah, max 10.
Oh, okay.
Yeah.
Why don't you like choose it stochastically, like see it as a distribution?
Okay, so recall that to have rollout performance guarantee, you need deterministic, right? You need to have, okay, this get a little bit technical. So for rollout to have performance improvement, to have the proof go through, you need to have this, let me go to this place. Essentially, it's this inequality, right? You would like to have the performance rollout improve upon the greedy policy. And one key step is this inequality. Let's say this inequality holds. To have this inequality, that means you need to have the selected control you choose better than the greedy policy in this formula. But if the greedy policy is not even one among the ones you choose from, you don't really know whether or not you improve upon it. On the other hand, you might consider using some stochastic based heuristic, but essentially means you are doing something different, that all those deterministic simulation and so on are not valid anymore. You need to run many samples, average them over, and so on and so forth. And that's a completely different topic or different choice. From theoretical point of view, it would still hold if you run Monte Carlo simulation and average them over with performance improvement and so on. Yeah, but that's different. Yeah. Okay. So in the next lecture, we're going to talk about other neural network and approximation architectures. We're going to touch upon offline training and the use in RL context. So this part of the material is covered in the chapter 3 of the textbook. All right.
Thanks.